Hello everyone, welcome to today's video. We're going to be going over the pre-algebra section of the ACT Math in terms of content areas. Remember, this is the first one of the 7 main content areas. So as you can see on the screen, these are the different subtopics that we're going to be working through. So let's go ahead and get started with types of numbers. So I have my whiteboard here. So types of numbers, we'll start with what are integers. Basically, integers are any number that's like, it's a whole number. It's not a fraction or a decimal. So like 2, 5, 10. These are examples of integers. All right, now we can move on to rational numbers. Rational numbers are any numbers that can be expressed in a ratio. So for example, we can have fractions and decimals here. So like 1/3 or 0.8 or -2. These are all examples of rational numbers because we can write these in the form of ratios. Now, irrational numbers are the opposite of this because these are going to be numbers that you can't express in a finite ratio. So, for example, like pi, right? Pi keeps on going. It's 3.14159. It never ends, right? Another example is like the square root of 3. That's like 1 point something, and it keeps going on and on. So you can't write it effectively as a ratio. So that's kind of the difference between rational and irrational numbers. Then we have real numbers. Those are different from, complex numbers. So real numbers are just any numbers that we can express, again, like 25 or 30 or something like that. Complex numbers, they have that I, which we will get to in a later section. But that's what real numbers are. Positive numbers, they're greater than 0, so like 2, 5, something like that. Negative numbers are less than 0, so like -2, -10, numbers like that. And then consecutive numbers, those are numbers that are in sequential order. So like 1, 2, 3, 4, like that. It's going up or it can be going down in sequential order. That's what consecutive numbers are. So moving on to the next topic of factors. What are factors? Basically, factors are numbers that your initial number is divisible by. So if we have, let's say, 20, right? What is 20 divisible by? Obviously 1. There's also 2, 4, 5, and then 10 and 20. And it makes sense, right? Because these, if you were to do 20 divided by 1, you'll get a whole number. 20 divided by 2, you'll get a whole number. So if you divide your original number by its factor, you should get a whole number. That shows that that number is a factor in this case. Okay? So moving on to the next section, we have prime numbers. So prime numbers, these are numbers whose only factors that they have are 1 and itself. So for example, 13, that's a prime number. Obviously, 1 and 13 are factors of it, but does anything else divide evenly with 13? If we try 2, no. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. If you were to divide 13 by any of these numbers, you're not getting a whole number. So therefore, it's a prime number. It only has 1 and itself as a factor for that number. So then moving on to prime factorization, what we're doing is we're basically taking a number and we're kind of breaking it down into its prime factors. And then when you multiply those prime factors together, you'll be able to get that number. So for example, let's say we have the number 80 and we want to do the prime factorization of 80. So let's first pick two factors of 80 that we know. Okay, 80 is even, so I'm going to start with 2, and then 80 divided by 2, that gives us 40. All right, so 2 is a prime number because there is no other number that divides evenly with 2 that's not 1 or itself. So 2 is a prime number. 40, though, is not. It's another even number. So again, I'm going to do 2, and I'm going to do 40 divided by 2, which would be 20. Again, 2 is a prime number, but 20 is not. So we can follow the same process because it's still even. 2 and 10. All right, 2 is prime, 10 is not. Again, it's even. We have 2, and then we have 5. 2 again is prime. 5 is also prime because, again, there's no other number except 1 in itself that would divide evenly into it. So 5 is a prime number. So since we have both prime numbers now, we can't break this number down anymore. So we have 4 2s, so we can write it as 2 times 2 times 2 times 2, and then this other 5 here times 5. Okay? And what we can do is we can actually, since we have these repeating 2's, we can actually make it into an exponent form and have it as 2 to the 4th power times 5. Right? That's the same thing because we have 4 2's. And it makes sense, right? If you were to multiply this out, you should get 80. So 2 times 2, that's 4, times 2, that's 8, times 2, that's 16, times 5, that gets us 80, our original number, which is exactly what we want. So that's how you would prime factorize a number. You're breaking down a number into its factors until you're down to just prime numbers, and you can rewrite it like this. All right. So let's move on to the next topic, which would be least common multiple and greatest common factor. So least common multiple, you're given 2 or more numbers and you're trying to find the least common multiple, meaning what number is, if you were to like multiply a number by that number, you should be able to get that multiple. It's greater than the numbers that you're dealing with. I know that sounds a little bit confusing right now. So let's go through an example. Let's say we have 8 and 10. And we want to find the least common multiple between them. Probably the best thing to start doing right off the bat is we can, just to illustrate it first, we can try to list out some factors of 8 and some factors of 10. And the first multiple, not factor, first multiple that is common between the two, that would be our least common multiple. Once we go over GCF, there's a little interesting strategy you can use to get the least common multiple faster, but we'll get to that in a second. I want to just illustrate it out for you guys first. So let's start with multiples of 8. So basically 8 times 1, that would be the first multiple of 8. So that's 8. Then 8 times 2, that's 16. 8 times 3, 24. 8 times 4 is 32. And then 8 times 5 is 40. So that would be, let's say we're just going to do the first few multiples of 8. And then let's try the first few multiples of 10, right? So 10 times 1, that's 10. 10 times 2, that is 20. 10 times 3, that is 30. 10 times 4 is 40. And then let's say 10 times 5, that is 50. So we see that 40 matches up in both multiples of 8 and 10. So since that is the first multiple that these two numbers share, that is your least common multiple. So 40 would be the answer. That would be your LCM of these two numbers, 40. All right, let's say now I wanted to find the GCF. So GCF stands for greatest common factor. So remember, numbers that these two are divisible by. So what is 8 divisible by? 1, 2, 4, and 8. And then what is 10 divisible by? 1, 2, 5, and 10. Oops. That was pretty bad 0. 10. All right. So what is the highest factor that these two numbers share? Obviously, they both share a 1, okay? They also both share a 2. But they both don't have a 4, they both don't have a 5, they both don't have an 8, and they both don't have a 10. So 2, that would be our greatest common factor. So our GCF would be 2, okay? So the strategy that I was alluding to earlier, you can actually get your least common multiple a lot faster than having to actually go through factors. What you can do is this. You can multiply these two numbers together and divide by their GCF. Really think about it, right? If we do 8 times 10, we get 80. And if we divide it by 2, which is the greatest common factor, we get 40, which is our least common multiple here. We'll work it out with another example just to show you guys that it works. Let's say we have, I want to pick one with a good GCF between the numbers. Let's go 6 and 16 for the sake of it. Actually, no, I want one with a 3. Okay. New plan. I want to get a good GCF that's higher than 2. Let's go 6 and 21. let's go 6 and 21. I want to give you guys a higher GCF than just 2. So we can multiply these two numbers together first, right? 6 times 21, that gives you 126. And then what's the GCF between 6 and 21? So 6 factors of 6, that's 1, 2, 3, and 6. And for 21, it's 1, 3, 7, and 21. So 3 is your highest greatest common factor between the two. That's why it's the GCF of both numbers. So we can divide this by 3, and we get 42 as our least common multiple. And that makes sense, because with 6, our first multiples are going to be 6, 12, 18, 24, 30, 36, 42. Well, with 21, we have 21 and then 42. So it works out like that. So this is a strategy you can use to find the least common multiple pretty quickly without actually having to lay out a lot of different numbers. And if you are doing the least common multiple or greatest common factor for more than 2 numbers, you can follow the same strategy as well. And same thing with the greatest common factor. You can just find the factor that is the greatest that is in common with all the numbers. All right. Now, order of operations. This one is pretty important. So order of operations, right? We've all heard of PEMDAS. PEMDAS. Okay. So what does that mean? The P stands for parentheses. So anytime you see numbers in parentheses, so if it's like parentheses 5 times 6, you're doing that first because it's in parentheses. Parentheses takes higher order than multiplication. The E stands for exponent. So if you have like 2 to the 4th, that would be an exponent. You try to evaluate that before you do any of the other stuff. The M stands for multiplication. The D stands for division. These are interchangeable, meaning the first time when you read a mathematical statement from left to right, you would do the whatever between multiplication and division, whatever comes first, you would do that first before getting to the other one. And then addition and subtraction, those take the least precedence. Again, just like multiplication and division, it's whatever comes first, that's what you're doing first. So if you see subtraction before addition, you're doing the subtraction first because it came first in the statement. So let's work through an example. Let's say we have 5 plus 8 minus 3 times 5 plus 2 to the 4th. Okay, let's start with this. So parentheses, we want to do that first. So 5 plus 8, that's going to give us 13. All right, and we can rewrite this once we evaluate the exponent, because that would be next. 2 to the 4th, that is 16, right? That's 2 times 2 times 2 times 2, which would give us 16. So minus 3 times 5 plus 16. Now we want to evaluate the multiplication that comes up next. So it'd be 13, 3 times 5 is 15, so minus 15 plus 16. And then now, like I said earlier, we're left with just addition and subtraction. So we're doing it from left to right. So we do the subtraction first. Negative 2, that's what 13 minus 15 is. Negative 2 plus 16, which when we add these two together, we get 14, which would be the correct answer in this case. So remember, PEMDAS for order of operations, you're going parentheses first, then exponents, then multiplication and division, depending on which one is first in the expression, and then addition and subtraction, whichever one is first in the expression is the one that you evaluate first. Okay, next topic, fractions. So fractions, these are basically a numerator and denominator, so it's basically two numbers divided by each other. That won't give you a whole number. So we have, let's say, 2/5, right? So this number 2 at the top, I really should actually write it like this so it's a little bit easier to understand. This number 2 at the top is your numerator, right? That's just the number at the top of the fraction. And the 5 in the bottom, that would be your denominator. So that's what fractions are. We're going to do adding, subtracting, multiplying, dividing fractions first, actually, because we're on the topic of it. So how do we add and subtract fractions? we basically want the denominators to be the same when we add or subtract fractions. So for example, if we have 2 over 5 plus 1 over 3, the answer is not 3/8. You're not adding these, like adding the numerators, adding the denominators. You can't do that. You need to have the denominators be the exact same before you can start adding the numerators. So this goes back to finding the least common multiple, right? We want the least common denominator between these two fractions, so that way we'll be able to add up the numerators. So least common multiple between 5 and 3, easiest trick, just multiply it out. 5 times 3 is 15. Highest factor between the two is 1, so 15 is the common denominator we are working with. So now we need to rewrite each fraction with a denominator of 15. So when we are multiplying, right, we had to multiply these fractions, these denominators, by a certain value to get 15, and we have to do the same to the numerators to make sure that these fractions are equal. So how do we get from 5 to 15? We multiply the denominator by 3. So we're going to do the same to the numerator. We're going to do 2 times 3. That gives us 6 on the top. And then for this fraction, how did we get from 3 to 15? We multiplied the denominator by 5. So when we do 1 times 5, we get 5 at the top. So 6 plus 5, that gives you 11 in the numerator. And you're not adding these denominators. That would just be what is your denominator. Once you get a least common denominator, that would be your denominator. And you're just adding the numerators. Same thing works if you are subtracting fractions. Just for the sake of time, let's say I change this to a minus sign, right? Now here, it's the same conversions because it's the same problem. I just changed the sign. So we put a minus here. So again, the denominator is staying the same, but this time for the numerators, you're going to be subtracting the two numerators. So 6 minus 5, that gives us 1. So 1 over 15, that would be the answer for the subtraction problem. All right. When we're talking about multiplying and dividing fractions, it gets a little bit different. I'll change the problem for you guys this time, so it's somewhat different. Let's do 4 over 7 times, let's go with 3 over 8. So when we multiply fractions, yes, we can multiply the numerators and multiply the denominators together. But typically when we want to do problems like these, we want to simplify it early so that way we can get to our final answer quicker. So if you were to multiply this straight out, right, 4 times 3, you'll get 12 in the numerator, and then 7 times 8, you'll get 56 in the denominator. Obviously, that's not fully simplified because there's a GCF in both the numerator and denominator. It's a common factor that you can cancel out to simplify it. We're going to go ahead and take care of that while we're multiplying here. So when we're trying to kind of reduce numbers when we're multiplying, we're working cross. So we're trying to look at if there's a GCF between 3 and 7 that's greater than 1, and if there's one between 4 and 8 that is greater than 1. Oh my god, that was really bad. Between 4 and 8 that we can, reduce these fractions to. So 3 and 7, their GCF is 1, so we can't really do anything. However, 4 and 8, their GCF is actually 4, because the factors of 4 are 1, 2, and 4. And for 8, it's 1, 2, 4, and 8. So we can actually divide both these numbers by 4. So we have a 1 in the numerator now, and we have a 2 in the denominator, because 8 divided by 4 is 2. So now we can just multiply these now. 1 times 3, that's 3. 7 times 2, that's 14 in the denominator. So 3 over 14, that would be your final simplified answer. If it's a little confusing, of course, you can just multiply these original numbers straight out and then do the GCF at the end, but I think it's better to just do it earlier so that way you'll be able to get the answer faster. So remember, when you're trying to cancel out GCFs before you multiply, you're doing it cross. So basically top left, bottom right, and bottom left, top right. Those are the ones that you're going to be doing for canceling out factors. Now let's say we want to divide a fraction over another fraction. Let's say we have 3 over 5 divided by 2 over 9. So here we're doing keep, change, flip. So we're going to keep this first fraction here, right? 3 over 5. We are going to flip this division sign. I'm sorry, we're going to change, my bad. We're going to change this division sign into a multiplication sign. By the way, for multiplication signs, try not to use this because we're going to get into variables in a later video, and x is typically a variable that we use. So for multiplication, instead of using this x, use the dot. That simplifies multiplication. Sorry for not saying that earlier. So we're going to change this division sign to a multiplication sign, and then we are going to flip this denominator, 2 over 9. We're going to flip the numerator and denominator. So now we're going to make it 9 over 2. All right. We can quickly look to see, is there a GCF between 3 and 2 that's greater than 1? Nope. 9 and 5? No. So we would just multiply these numbers straight across. 3 times 9, 27 in our numerator, and then 5 times 2, 10 in our denominator. So that would be the answer. So dividing fractions, always remember keep, change, flip. You're keeping the first fraction the same. You're changing the division to a multiplication, and then you're flipping this denominator, the second fraction, so it can just become a multiplication problem. So 27 over 10. And that actually is going to bring us straight to our next topic of mixed numbers and improper fractions. So let's say we have this number 27 over 10. I'll rewrite it in the middle. 27 over 10. So this is an improper fraction because the numerator is bigger than the denominator. A proper fraction is when the numerator is less than the denominator. So typically when you're multiplying fractions, you want to deal with improper fractions more than mixed numbers. But to illustrate mixed numbers, what are mixed numbers? They have a whole number and a fraction component. So basically we kind of want to reduce this to a proper fraction with a whole number attached to it. So how would I do this pretty quickly? I want to find out the whole number first. So what's 27 divided by 10? If we were to do that, what would be the whole number attached to it? Well, 20 divided by 10, that's 2, right? 30 divided by 10, that'd be 3. That's a little too big. So 2, that would be our whole number. So then now, how do we get the proper fraction? Well, we just took out 2, right? 2 is the same thing as 20 over 10. So I do 27 over 10 minus, oops, that was pretty bad, minus 20 over 10. And remember, we're subtracting fractions, so it's going to be keeping the denominator the same and just subtracting the numerators. So we get 7 over 10. So that would be the proper fraction part that we're attaching to the whole number. So this is an example of a mixed number here. You have a whole number component right here, and you have your proper fraction component right here. Okay? We can try one more example just for understanding. Let's say we have 36 over 5. Again, what would be 36 divided by 5? Right? So what is the whole number? What's the closest multiple of 5 to 36, right? We have 5, 10, 15, 20, 25, 30, 35, 40. So 35, it needs to be less than the actual number you're dealing with. So 35 divided by 5, that is 7. And then to find the proper fraction component, 36 over 5 minus 35 over 5. That gives us 1 over 5. So that would be the proper fraction component. 7 and 1/5, that would be your mixed number. All right, let us move on to the next topic of scientific notation and place value. So what is scientific notation? Basically, you have a number or a decimal that ranges anywhere from 1 to 10, right? 1, let's say x is your number, and 10. Try not to have it as fractions because it doesn't make sense. You want to use decimals or whole numbers, and you're basically multiplying it times 10 to the power of something. Let's just call it n. So for example, let's say we have 4 times 10 to the 5, right? That's an example of a number written in scientific notation. 4 is between 1 and 10. and it's multiplied by some power of 10. So it's really important to be able to kind of convert back and forth between regular numbers and scientific notation. So let's say we have 2, and let's say we add, just add 6 zeros, right? Let's say we're asked to write this number in scientific notation. So we want our number to be in between 1 to 10, so 2. Right now, let's say we imagine it as a decimal place, right? The decimal place right now is right here. So we want to move the decimal place to get it to 2. So we'd move it back 1, 2, 3, 4, 5, 6, right here. I have no idea why it went to a line. But that's the idea. You're counting back the number of zeros, moving the decimal place so it can get here. So you have 2 times, how many times did we move the decimal place to the left? We moved it 6 times. So that would be your n. So times 10 to the 6. So that would be how you'd write this in scientific notation. Now, what happens if we do it the other direction? Let's say instead of having a positive exponent here, we have a negative exponent. So how does this happen? Let's say we have a decimal, 0.00001. So now, instead of moving the decimal place to the left, where we'd have a positive exponent, we're moving the decimal place to the right now. So we'd move it to the right 1, 2, 3, 4, and 5. Remember, 0.1 doesn't count. It needs to be in between 1 to 10. So right here, that's where the new decimal place is. So it'd be 1 times, how many times would we move it to the right? 1, 2, 3, 4, 5. So times 10, and since we're moving it to the right, it would be negative 5. And that makes sense, right? If we were to actually multiply this, we'd get this number at the top here. It's also important to be able to multiply and divide and add and subtract scientific notation. We're going to go over multiplying and dividing first, since that's a little bit simpler. Let's say we have 4 times 10 to the 5, and we are multiplying it times 2 times 10 to the 8th. All right? When you're multiplying the whole numbers together. So 4 times 2, that's 8. And then when you multiply these powers, these exponents, you're adding the exponents together while keeping the base the same. So 8 times 10 to the 5 plus 8 power, which is 13. If you do multiplication, and let's say you get a number that's like here, your whole number, it's greater than 10, then you would adjust it to make sure that it does follow scientific notation. So if you got, let's say, 80 times 10 to the 13, right, you'd have to change it to 8 times 10 to the 14, right? It's almost like you're breaking it down into 8 times 10 times 10 to the 13, right? And we can rewrite this 10 as 10 to the first power, so you just add these exponents together and get 10 to the 14. All right, dividing, very similar. We have, let's say we have 2 times 10 to the 10 over 4 times 10 to the 5. And I'm saying similar because you're basically doing it whole number by whole number, exponent by exponent. So 2 divided by 4, that would be 0.5, because that's the same thing as 1 over 2. And then times, when we're dividing exponents, we'd actually be subtracting the powers. So 10 minus 5, we're keeping the base the same. 10 minus 5 would be 5. And again, if we were to have it be where the whole number is greater than 10, you just adjust it accordingly. All right, adding and subtracting scientific numbers, that's a little bit trickier because you can't just, add them together like we did initially. So for these ones, what you have to do is you have to get your power of 10 to be the same for both the numbers, and then you can add them together. So let's say we have 4 times 10 squared plus 5 times, let's go 10 to the 1. I'm going to start with something really small just to kind of illustrate it first. So we have 4 times 10 to the 2 and 5 times 10 to the 1. So these are different powers. So we're going to want to change it to make sure that we're able to get both in the correct power. So in this case, what we'd want to do is convert this 5 times 10 to the 1, we can actually, since it's a smaller number, we can convert it to 50, right? Because that's what 5 times 10 is. And then here, we can make it 400. So when we add it together, we get 450, right? Which if we rewrite it in scientific notation, the decimal point is here. We want to move it back to 4.5, and then be times 10 squared. So how could we do this here without having to work this out? Let's say if you have higher exponents, you'll want to convert this to the higher power. So in this case, we have 5 times 10 to the 1. This has the lower power right now. So how do we get 10 squared? If we are going to multiply this part by 10, we have to divide this part by 10. So that way we're keeping it fair, right? So if we multiply this part by 10, we get 10 squared. We have to divide this part by 10 to get 0.5. So now we have 0.5 times 10 squared plus 4 times 10 squared. We can add these whole numbers to get 4.5 and keep the exponents the same. Same applies if we're doing it as a subtraction, right? I'll keep these numbers the same. I'll change the sign. So let's say we make this a minus now, right? Again, you're following the same steps. You want to convert this to the same power, the higher power, and then you just subtract the whole number. So you get 3.5 times 10 squared. Obviously, you might deal with higher powers than just 1 and 2, but I just wanted to illustrate it out for you guys. So now let's get to place value. What is place value? That's what each value in a number signifies. So let's say we have 251.25. So we'll start with the whole numbers on the left side of the decimal place first. So this first number in front of the decimal place, that's called your ones place, right? Then the number to the left of that is the tens place. Then you have the hundreds place, thousands place, 10,000s place, and so on. It's basically a multiple of 10. So this would be 10 to the 0. This would be 10 to the 1. This would be 10 squared, and so on and so forth. That's what the value, that's what it signifies, right? Now, let's say we're on the right side of the decimal place. This here would be our tenths place, like T-E-N-T-H-S, tenths place, because this would be 10 to the negative 1 for the value of its place. This would be the hundredths place, because this would be 10 to the negative 2, or 1 over 100. So that's how you remember. That's basically what place value is all about, knowing what each number in a particular number, what each individual number, what it represents place value wise. So you have your decimal place. Numbers to the right of it are going to be, representing like 10 to the negative 1, 10 to the negative 2 in terms of their place. And to the left, it would be ones, tens, hundreds, so on. Here would be tenths, hundreds, thousands, and so on, like that. Okay, next topic, percentages. So percentages, what is a percentage? Basically, it's a number that if you were to divide it by 100, you'd get its decimal value. So let's say we have 25%, right? It's out of 100. So if we were to convert it to a decimal, 25 divided by 100, we would get 0.25. Right, so that's what percentages are basically. It's a good way to convert between decimal and percentages as well as fractions. You can use these interchangeably, and they can ask you that on the ACT exam. Another example, let's say we have 0.43, right? We can multiply this times 100 to get a percentage, which would be 43%, because when we're multiplying times 100, we're moving the decimal place to the right 2 times. 43, and then we'd slap on a percentage sign at the end. So it's important to be able to know how to convert between percentages, decimals, and fractions. All right, next I believe was ratios and proportions. So this is kind of similar to what we were talking about with fractions, where you have, like, let's say a part over a whole. So your numerator would be your part, and your denominator would be your whole. And then proportions would be like, let's say 1:4, right? You can rewrite it as 1/4, something like that. So it's basically, you can interchange between these two, but ratios are really going to be helpful when you have different word problems, which we'll talk about word problems in a later video. But when you have, like, let's say when you're wanting to make something and you need one part flour to 4 parts sugar, something like that. This is where your proportions would come in handy. This would be your proportion of sugar, or flour in this case, and sugar. And you can multiply these proportions by, let's say, like 2, and you're multiplying each part of the proportion by 2, so you'd have 2:8. The proportion needs to stay the same, even if you're multiplying it times, let's say you want to make like 2 batches. So your proportion would be, for the entire thing that you're making, it would be 2 parts flour to 8 parts sugar. You want to keep the proportion the same. All right. And then finally, we have absolute value. What is absolute value? It's represented by these double bars, and it basically means that whatever is there, it's going to return the positive value of that number. So if we have negative 10 in absolute value bars, the answer for that would be 10. If we have 3 in absolute value bars, it's going to be 3. The positive equivalent is what it's going to be for the answer. We can even have problems inside here too. Let's say we have negative 5 times 6, right? What's negative 5 times 6? Well, 5 times 6 is 30. One of them is negative, so it's going to be negative 30. But we have the absolute value bars on the outside. That is going to make it 30. So that's what absolute value is. You're taking whatever number, whatever expression you get inside of the absolute value bars, and you're making it positive. All right, so that is all the major pre-algebra topics you need to know on the ACT Math exam. This is typically your easiest content area on the ACT Math exam. These questions you should be going pretty quickly, because the later sections, those are a little bit tough in terms of, needing to know content / the problems taking more time. So we're going to pick up with elementary algebra in our next video. Be sure to like and subscribe, and if you need anything, please feel free to reach out. Thank you.